let me show you how we can eliminate, or at least minimize, the effect of air resistance in the following way. Here is a book, and here is a sheet of paper. Let me start them at the same height and drop them at the same time. You see the book plummets straight down, and the paper just floats down. Now, if I'm going to reduce the effect of air resistance on this piece of paper, let me crumple it so it forms a more compact mass. And now let's watch what happens when I drop these two again. You see they fell much more nearly alike, and in fact, if I go still farther and crumple this into a very dense, compact wad, I think you'll see that by so doing, we have virtually eliminated the different effect of air resistance on the book and on the sheet of paper. Now, this is really a remarkable thing. Here, a sheet of paper, only one tiny fraction of all the sheets of paper which go to make up the book, plus the hard covers, perform identical motions in the absence of air resistance. But this remarkable fact is not confined only to a sheet of paper and a book. Any object, this pencil, this croquet ball, this lead brick, block of wood, cigarette lighter, comb, anything you imagine. If we let these bodies fall freely in vacuum, or what is the same thing, under such conditions that air resistance is negligible, they all fall with the same accelerated motion. During the past few weeks, we've learned that to accelerate a body, it takes a push or a pull. And when this push or pull is in the direction of motion, the force is related to the acceleration of the body by Newton's law of motion. F equals ma. You notice I put a subscript I on the m, and this is to remind you that this mass is the inertial mass of the body, a dynamical property of matter. For the case of freely falling bodies, we already know the acceleration. Do we know anything about the left-hand side of this equation? The force F, which produces the acceleration of freely falling bodies. Yes. This force is the gravitational pull of the Earth on a freely falling body in the case where the air resistance is negligible. Earlier, we used this same gravitational pull of the Earth to establish a measure for another different property of matter. This property is the gravitational or chemical mass of a body. To do this, we used an equal arm balance, such as this. When the balance is in equilibrium, the gravitational pull on each of the bodies in the two pans is equal. And this establishes the equality of gravitational mass. Now, this equality does not depend on where we do the experiment. Equal gravitational mass will balance no matter where you do it. In this room, on the top of the mountain, even on the moon. Now, the actual gravitational force on a body depends on where you are. But in any case, this gravitational force is proportional to the gravitational mass of the body. If we write this proportionality in the form of an equation, it looks like this. Gravitational force is equal to a proportionality constant G times the gravitational mass of the body which is being pulled. This G is called the field strength of the gravitational field produced by the attracting body. It is the force per unit mass with which the attracting body pulls on any object. And it depends on the location of the object. It's smaller on the top of a mountain than it is in this room. The field intensity of the moon at its surface is only about 1/6 of the field intensity of the Earth at its surface. Now, here are two expressions equal to the same thing. the gravitational force. Therefore, they are equal to each other. There it is on a card. Now, little g, gravitational field strength, doesn't depend on the body. It's the same for all bodies. It depends only on the thing that does the attracting, not on the body that's being pulled. We have found out experimentally that the acceleration of freely falling bodies doesn't depend on which body falls. It's the same for all bodies. Therefore, no matter what body we're talking about, gravitational mass is proportional to inertial mass. And here it is written up. This is an amazing characteristic of matter. There's no reason beforehand why you should suspect that that property of matter, gravitational mass, which tells you how hard some other material body pulls on it gravitationally, should have anything to do with inertial mass, MI. That property of matter which tells you how much acceleration that body will get when you pull on it with any kind of force. Actually, if we use for both these masses, which are now proportional, the same unit, the standard kilogram, then the numerical values become equal, and we say that gravitational mass equals inertial mass. Now, this experimental equivalence between these two different properties of matter, gravitational property on one hand, inertial property on the other, is really the reason we use the same word mass for both these quantities. Now, what else can we learn by studying the motion of freely falling bodies? As long as we confine ourselves to looking at motions that are along a vertical line, whether we throw a body straight up or down or let it fall from rest, there's not a great deal more of interest. However, if we look at this motion of a falling body, here's a piece of chalk. There's a motion different from any we've met. It's motion in a curve, and this is the first time we study such motion. During this motion, the gravitational pull of the Earth is straight down. It has the same value at each point of the motion, and furthermore, the direction of motion is different from the downward direction of the force at every point. We now ask the following question. Does this downward gravitational pull of the Earth produce the same downward acceleration for the curved motion as it did for a body falling freely from rest? There's only one way you get an answer to such a question, and that is from experiment. Let's first try a simple experiment. Let me take a couple of coins, $half, place them at the edge of the table, one slightly behind the other. I will now flip these off the end of the table so that one coin will just fall over the edge and the other will be projected with a relatively large horizontal motion. I want you to listen for the sound when these two hit the floor. Here we go. One sound, not two. It took just as long for the coin which was projected horizontally to hit the floor as it did for the one which fell straight down. Now, this equality of the time of fall for both these coins suggests that maybe the vertical motions are identical at all instants of time. Let's do another experiment to see if this is really so. Instead of the two coins, I'm going to use these two balls, one of which is hanging here on a magnet, and the other I will project horizontally by sliding along this trough. Now, to make sure that they start at the same time, there is a switch here which will break the circuit holding the ball, and as you see, when this ball leaves the trough, just at the instant it starts falling, the other one falls. They start at the same height at the same time. We're now ready to do this experiment, and I want you to watch the vertical motion of both these balls and compare them as they fall. There you see the motion of the two balls, one projected horizontally, the other dropping from rest, and both starting to drop at the same time. Now, in order to see the details of these motions and to compare them, let's watch them in slow motion. Keep your eye on the vertical height of each ball at each instant of time. Now, to go one step further, we're going to repeat this experiment and show you pictures of the position of each of these balls at equal time intervals. On each of these pictures, you see drawn a line tangent to the bottom surface of each of these falling balls. Each of these is horizontal. This means that in equal times, both bodies have fallen the same distance, exactly. The vertical acceleration produced by the pull of the Earth on each of these balls is exactly the same, although one is moving with a horizontal speed and the other is not. But there is more that we can get out of these pictures. If we look at the horizontal motion of the ball I projected and construct vertical lines tangent to this in each one of our still shots, we see that these vertical lines are equally spaced. This shows that the horizontal motion of the projectile was one of constant speed, unaffected by the vertical downward pull of the Earth. Our general conclusion is then that the vertical accelerated motion of a freely falling body is unaffected by what goes on horizontally, and the uniform horizontal motion of a projected body does not depend at all on the fact that it simultaneously undergoes vertical acceleration. Now, using Newton's law of motion, we can find out something more about the nature of inertial mass. You notice I have added arrows over the force and the acceleration in this formula. The reason is that we have determined experimentally that force is a vector, and we know that acceleration is a vector from its definition. Now, what we have found out from our experiment is that the vector force and the vector acceleration are in the same direction no matter which way the body moves, no matter what the direction of motion is. From this, we can conclude that this inertial mass, that quantity, does not depend on the relative direction of motion and force. This leads us to suspect that maybe the inertial mass doesn't depend on direction at all, that it has no directional properties. You can't prove this completely by just looking at falling body experiments, but other experiments do confirm this notion. Mass is a scalar quantity. Now, we found out something else in addition. You remember that the horizontal motion of a freely falling body was independent of the vertical motion. What happened vertically had nothing to do with what was happening horizontally. This is true in general about curved motion. The component of any motion in a fixed direction in space is independent of the component of motion at right angles to the first direction. This mutual independence of these two components of motion enables us to solve problems in a rather simple way, which otherwise would get somewhat involved and complicated. Let me take a simple example to show you how this goes. Imagine you're in a jungle hunting monkeys, and you come across one hanging from the limb of a tree. Now, let's suppose that when you fire at this monkey, at the flash of your gun, he lets go and starts dropping. The problem is, where should you aim to ensure a hit? Now remember, you don't know how far you are from the monkey. He may be above or below you, and you have no idea what the muzzle speed of the bullet is which leaves your gun. Now let me show you how one uses the independence of vertical and horizontal motions to solve this apparently complicated problem. To make life easy, let's start with a simple case. Now first, let's consider the simple case where you and the monkey are at the same height. Suppose this represents the position of the gun, and this, the position of the monkey. If, for a minute, let's imagine that the force of gravity does not act, then you know very well how you should aim to hit the monkey. You aim horizontally, right at the monkey. The bullet travels in this straight line, and you hit the monkey. Now what happens in the real case where the earth pulls on both the bullet and the monkey? We know that the vertical motion produced by this downward pull is the same for both. The horizontal speed of the bullet determines how long it takes for the bullet to travel from the gun to the line of fall of the monkey. And in this time, the monkey falls, let's say, down to here. During this time, the bullet undergoes the same vertical motion as the monkey and will follow a path something like this, falling exactly the same distance, and we get a hit. So you see, for this simple case, the way to hit the monkey is to aim at it. How about the more complicated case where the monkey is not at the same level? Let's say he's above you. Let's take a look at this one. If, again, this represents the location of the gun, and this, the location of the monkey, hanging from the limb of the tree, you remember. Once again, if gravity were not acting, we would again aim at the monkey. The bullet would travel along the straight line, joining the gun and the monkey. Notice that in this case, the muzzle velocity of the bullet, which I'll represent by this vector V, has a horizontal component so. And this horizontal component determines how long it takes for the bullet to reach a vertical line drawn through the monkey. The vertical component of velocity, which is proportional to the horizontal component, ensures that the bullet will rise just exactly the right amount to cross this vertical line at the height that the monkey is. All right, what happens now in the real case? In the real case, you fire, the monkey starts falling. In a certain time, a time determined by this component of muzzle velocity and this distance, the monkey will fall to here. The bullet will no longer travel along this straight line, but will have a vertical downward acceleration exactly the same as that of the monkey. In the same time, then, the bullet will follow a path something like this and will end up below this point, which it would have reached without gravity, at a distance below it just exactly the same as the distance the monkey's falling. So you still get a hit. The answer, then, is extremely simple. If you want to hit the monkey, you just aim at it. In fact, it's a lot easier to hit a target which starts falling from rest when you fire than it is to hit a stationary target. Now, does this really happen when you do an experiment? Well, we're not going to shoot a monkey, but we're going to do an experiment which does exactly the same sort of thing. This magnet and ball, which you've seen before, now represent the tree and the monkey. The guns are to give different speeds and be aimed, as we will see. This is an old-fashioned crossbow made out of a leaf of an automobile spring. Here you see a pair of gun sights being mounted so that we can aim the gun properly. As you see, they are adjusted so that we aim the center of the ball. Now, we're sighting through these sights, and you see we aim at the center of the ball that represents the monkey hanging on the limb of the tree. make sure the monkey starts falling when the gun's fired, we use this switch, very similar to the one we used before. Now, let's change the muzzle speed of our projectile. Move the monkey up. There we are, hoisting the monkey, or pushing him up, rather, and attaching him to the limb of the tree, the magnet up near the ceiling. Here's the shot, and it's in slow motion so you can follow it. Are we going to make it? Now, once again, let's take another look at this. Watch closely. Now, what have we learned today? First, we learned that all bodies, no matter what they're constituted of, in the absence of air resistance, fall with identical acceleration. This equality of acceleration for all bodies led us to the conclusion that gravitational mass, that property of matter which tells you how hard the Earth pulls it, is identical with inertial mass, of matter which tells you how hard it is for any force whatsoever to change its velocity. Now, you know very well that this acceleration of a freely falling body is constant. But this is relatively unimportant. After all, it only tells you how small you are compared to the size of the Earth. Secondly, from experiments with projectiles, we found that the horizontal and vertical components of motion were independent one of the other. What happened in one direction did not depend on what was going on in the other direction. This experimental evidence lends support to the idea that Newton's law of motion is really a vector law. And it's a vector law in which force and acceleration are the vectors, and mass is a scalar. This scalar mass has no directional properties and does not depend in particular on the relative direction of motion and force. Now, in addition, this independence of component motions along fixed directions at right angles to each other allows us to solve certain complicated problems of curved motion rather simply. You simply take one component of the motion, make believe all the others aren't even there, solve for it. Do this for each component and combine the results by vector rules, and there's the answer. And finally, and this is by far the least important thing we've learned, you found out how to shoot monkeys.
Have you ever wondered what would happen if everything in the world were suddenly 10 times smaller? times larger. How does this work? This scale model looks all right by itself, and so did the little faucet. But the water drop looked all wrong. It refused to scale down with the faucet. In this film, we want to study what happens when you change the size of objects, when you make a simple scale change, altering all the dimensions of something in the same ratio to get a similar object of a different size. And it's going to turn out that for reasons of the laws of physics, you can't just change the size of most things without at the same time changing their nature, or changing some relationships, like the relationship of the water drop to the faucet size. But the simplest things that we have to deal with, geometrical relationships, do not change when you change the scale. They remain unaltered. These cards show a well-known theorem in geometry that any triangle inscribed in a semicircle is a right triangle. And of course it's true whether you have a large circle or a small one. But this is a statement about idealized figures, which we can represent by these lines, and not about physical objects. A real physical object, I have some putty here, may not scale. It may not behave the same in a large and small version just because of some physical reason, such as inability to hold up its own weight. Now I'm going to make a little bar with some of this putty in this wooden form. And the form gives it, bar, a certain definite size. And I will make an arch out of it here. Here I have a form that's just 10 times larger than that one, 10 times longer, wider, and higher, with a bar of putty in it. Let's see what happens when we make an arch out of this one. It fails to hold up its own weight. Somehow or other, the strength of the big bar was not enough to keep up with its weight. We could show many examples of this failure of the strength of things to keep up with their weight. For instance, consider holding up a weight with a cord. That's something we can figure out. I have here an accurate 1/10 scale model of a steel safe with scaled down steel walls 1/10 the size of those of a real safe, and so on. This weighs 500 grams. Now I can lift this model easily with a nylon thread on this little winch, and I have strength to spare. Let's see how big that thread is. Just about 10 thousandths of an inch. I'll write that down. Now the question is, can I lift this 10 times bigger safe with a 10 times bigger nylon rope? That would be a cord 1/10 of an inch in diameter. Like this. Let's try it. What happened? Nylon's pretty strong, but it's not strong enough to lift this. When I change the scale factor by 10, going from the small safe to the big one, how much did the weight go up by? 10 times? 100 times? It went up, using the same materials, by 1,000 times, because the weight goes as the volume, and the volume goes as the third power of the length. If we just assume that these safes are cubes, then the volume of the safe, the volume of the little safe would be A cubed, where A is the side, and the volume of the big safe, 10A cubed, or 1,000 A cubed. The weight of the little one was 500 grams. The weight of the big one is 500 kilograms. The volume of anything goes up as the cube of the scale factor, including objects with holes in them. You might try to prove this for yourself sometime. Now, the reason that our cord broke is that the strength of a cord depends on its cross-sectional area and not on its volume. If we look at the end of a cord, we can see that there are a certain number of threads that are just proportional to the area of the cord. Bigger cross-section, more threads. This means that the maximum weight the thing can hold up, call it W max, is proportional to the area, that is, to pi r squared, where r is the radius. Now, if I multiply the radius by 10 to get a bigger cord, the area and therefore the strength will be 100 times the area of the little one. The strength has gone up by the square of the scale factor, whereas the volume and therefore the weight went up by the cube. This is the reason that anything, if you scale up its size, will eventually get too heavy for its strength. This turns out to be true also for legs or supports from below, and for any sort of shape. Now, what should we have done if we wanted to pull up our safe? We should have taken a rope whose cross-sectional area, if big R is the radius of the rope, was 1,000 times the cross-sectional area of the thread. This would mean a rope whose radius is the square root of 1,000 times R, or about 32 R. That means, since the diameter of the thread was 10,000ths of an inch, that we need a rope that's about 32/100ths of an inch in diameter, about 5/16ths of an inch. I have a piece of 5/16ths inch nylon rope here. That ought to do the trick. Good. Incidentally, we did weigh this safe, and it's pretty massive. 500 kilograms, it's over half a ton. Now you know something. If you want to make a structure larger, you must make its supports more than proportionately thicker, or else its strength won't keep up with its weight. For example, what about those huge monsters you sometimes see in the movies? In this old classic, King Kong was supposed to be a gorilla 50 feet high. Of course, his legs would never have held him up. The picture was faked by using a small-scale city as a background. Clearly, a real monster would have crumpled at once. And when someone says to you, "Look at an ant or a beetle. Isn't it wonderful? It can push around 10 times its own weight. Think of its strength if it were the size of a man," you can give him a little lesson in scaling laws and the strength-to-weight ratio. We can see how nature takes this kind of thing into account by looking at the skeletons of some small and large animals. All these animals are lightly and delicately made. At a much larger scale, see what happens to the supporting parts of the skeleton. More strength is needed, and since nature has only bone, muscle, and tendon to build with, she must thicken up the building materials. The largest land animals, big dinosaurs like old Brontosaurus here, were nearly too big to hold themselves up. And probably lived in a swamp where the water took some weight off their legs. It's clear why they could not have been much larger. But there are other kinds of limits on sizes of animals. There is no warm-blooded animal smaller than the little mouse-like shrew, and even he has a hard time staying alive. His trouble is not strength-to-weight ratio, but surface-to-volume ratio. This little hummingbird, like the shrew, has a large surface-to-volume ratio, which cools him off so fast that he can barely stay alive and has to spend most of his time eating. If we were scaled down by 10, that is 1/10 size, we too would be very worried about the heat loss effect, and also about some other things that we usually don't think about, like surface tension. Surface tension is the force that holds the surface of water or any liquid together, almost as though there were a skin on it. The balance between surface tension and the weight of the drop is what makes the drop the size it is. Surface tension is very important to things that are very small. Here, surface tension is holding up these water skater bugs as they skim along. They're not floating. They are standing on the water because their weight is too small to push the surface apart. A water surface will even hold up a solid piece of steel, if it's small enough. Like a needle, for example. Now, if I push the needle through the surface, it sinks. What is it that makes these surface forces so important for things at small size? You remember we said that when we scale something, the volume changes as the third power of a length. So that if you change the scale, you change the volume by the cube of the scale factor. Now, the surface is proportional to the square of the length. So that a scale change here changes the surface by the square of the scale factor. This means that if I scale down by a factor of 10, say, I will reduce the volume of anything by 10 cubed, or 1,000. Whereas I will reduce the surface only by 10 squared, or 100. This means that the force of surface tension, which is proportional to the surface area, will be 10 times more important compared to the weight. And of course, the effect is larger the greater the scale factor. The surface goes down all right, but the weight goes down even more, so that the surface forces become relatively more important. The fly has already figured this surface area to volume business out. His slightly sticky feet hold him to the glass. But if a mouse tried this, he would fail even if his feet were as sticky as the fly's. So far, we've learned that changing the scale of anything will probably change its behavior. Then what is the point of a working scale model? Can it be used for anything? Of course, scale models can be very useful tools, provided you know the physical laws that tell you how their behavior changes with scale. For instance, to interpret the motion of a model, you have to know how the scale of time changes as you change the length scale. Here is a laboratory devoted to the scientific study of model ships, rivers, harbors, and so on. By applying the laws of physics to observation of these scale models, research workers are able to predict the behavior of the real ship or river. Dr. Eagleson is looking at the performance of a new ship model in the towing tank.
Here we are studying the motion of a model ship in order to determine the performance of the full-sized vessel in a North Atlantic storm. This man is making last-minute adjustments to the model. At the end of the tank, another man controls the launching of the model, while the bank of electronic computers monitors the measurements that are taken. This machine is generating the storm waves. rapidly the model ship bobs up and down as it moves through the waves. Anyone who's ever been seasick knows the real motion is much slower. This is an illustration of scaling of behavior resulting from a geometrical change in size. As you will learn later, the time required for a simple clock pendulum to swing back and forth varies directly as a square root of the pendulum length. Ship oscillations are similar. In order to fit the model into this tank, we had to make it 1/100th the size of the actual ship. Thus, the model ship bobs up and down at the square root of 100, or 10 times faster than the actual ship. Here is a slow motion view of the same sequence, with time scale slowed down by 1 to 10. It looks more realistic, doesn't it? Here we have a hydraulic scale model of a destroyer base in Narragansett Bay, Rhode Island. It is constructed to a scale of 1 to 400. Natural waterways, such as harbors, involve such complex physical problems that mathematical description of their performance is not practical. However, a properly constructed and tested hydraulic scale model acts as a large computer, from which the performance of the true harbor may be determined by direct observation. The waves you see are such as result from severe winds. Notice the destructive violence of the ship motion near the docks. When a breakwater is properly positioned, the ship is shielded from wave action and motions are reduced to tolerable levels. This aerial photograph of the model shows clearly the protection that the breakwater affords. The best location and size for a multi-million-dollar structure such as this can be rapidly and accurately determined through use of scale models.
Another example of using the scaling laws, which are the laws of models, occurs in Hollywood motion picture production. Say we want to blow up a model bridge, which is a certain scale factor smaller than a real bridge. How would we make it look realistic? Well, the time it takes something to fall when you drop it depends on the square root of the distance it falls. So we would have to slow down the motion by some photographic trick by a factor which is the square root of the scaling factor. That's the same one that occurred in the case of the model ship. Now here is a shot from the film called For Whom the Bell Tolls. It was a small model, but the scaling laws were correctly applied. If we go up or down in scale from our ordinary man-sized effects, we have some ideas now what to look for. And these ideas work well as long as we don't change the scale so much that something really new crops up. But that is just what the scientist tries to do. He wants to go to the extremes of scale, not only of length, but of time or temperature, or any physical quantity that he can work with. He wants to push out to the edge of space, to the largest scale he can measure. And for that, he needs sensitive instruments, like this gigantic radio telescope at the Jodrell Bank near Manchester, England, which can receive and analyze radio waves from the farthest limits of the universe. By experiments on vastly different scales, the scientist is sure he will learn things that are new and vital for our understanding of our physical world. In our final example of a scale change, let's go in the other direction, down to the world of the extremely small. At the extreme of small distances, we find the basic structure of physics, the atom and its laws. That's a story you'll hear a lot more about later on in this course. What I want to point out now is that with an ordinary microscope, we can get down to a scale so fine that we can see the effects of atoms, even though we can't see the atoms themselves. We can see what happens when the atoms, which are always in violent motion in a liquid, push on a tiny speck, like a bit of this dye, which I have on the slide. By themselves, these specks are quite inert. But in a liquid, they begin to dance around in a very curious way. Watch the smallest ones. They move the fastest. Any tiny speck does this in a liquid. Why? It's much larger than an atom, but it is pushed by the atoms jouncing against it. A large object in water is pushed on by so many atoms that the average push is very steady. But a tiny speck is pushed on by only a few thousand, so that by accident, they often gang up on it, more on one side than the other, and move it around. You are seeing a direct effect of atomic collisions by going to this very small scale. Atomic physics, the heart of modern science, is being worked out with experiments which go down to scales far beyond the power of a microscope to measure. So we see that change of scale can mean many things, from a simple geometrical construction to a leap into a new and unfamiliar world, the frontier of science.
This film is about a new aspect of electrostatic forces. You've been used to thinking of these in terms of charges on objects which these objects exert on each other. Now we want to concentrate on something else, the region around the charges. Let me illustrate this at the blackboard. Supposing we have a few objects in space like this, perhaps marbles, with charges on them. We have learned how to describe the forces which they exert on each other. Let us now concentrate on a little region of space in which there are no charges. This may seem to you a strange thing to study. Perhaps you have thought that everything that science deals with is composed of the atoms on the periodic table. Here we have a list of all of them. Now we're going to consider the region between atoms. If you take them all away and have left only a vacuum, we find that there still is something about this vacuum which is worth studying. The aspects of a vacuum which we use in order to describe it are called fields. You've already discussed gravitational fields. Today we take up electrical fields and soon magnetic fields. And there are others. For example, in order to describe the motion of an electron in an atom or through space and reflected from a wall, we have to consider a new kind of field, a wave field. These fields are all very complicated. You may think that the atoms on the sphere here are executing very complicated motions and that this is a most complicated situation to describe. But it turns out that in a vacuum this is equally true. These fields, many of which are present in the same region of space simultaneously, are not only constant, but oscillate. We have oscillations of various frequencies of the electric fields, of the magnetic fields, of the wave fields of electrons. And in order to understand matter and the behavior of the universe all around us, we must consider these fields in some detail. But to begin with, we must take a simple example, namely the electrostatic field which surrounds charges, which Dr. Weymouth is describing here.
You're all familiar with the Coulomb's law representation of the forces between charged bodies. If I put similar charges on these two pith balls and bring them close together, they repel one another with a force that's proportional to the product of the charge on this one times the charge on that one, and inversely proportional to the square of the distance between them. Now, the idea of the electric field is that we can look at this force in a different way. We can consider that the force on this charge is due to the electric field exerting a force on the charge at this point in space, and that the electric field is produced by the charge on this pith ball. We can make this a little bit more quantitative by referring to Dr. Bitter's diagram. Suppose we would like to calculate the electric field in space inside this little box. But to do it, let us imagine that we put a positive charge in the box of size Q. Now, from Coulomb's law, we can calculate the force on that charge due to this one, and represented by an arrow, whose direction gives the direction of the force, one of repulsion, and whose length gives the magnitude of the force. Similarly, we can calculate the force on the test charge due to this one, and represented by still another arrow. And finally, we can calculate the attractive force due to this charge, and represented by a shorter arrow. Now, we know that the net force then on our test charge is the vector sum of these three forces, and it will be something in this direction. We can now define the electric field at this point in space in terms of our calculated forces by writing the vector equation E, a vector, is equal to the force on our test charge, which itself is a vector, divided by the size of the charge itself. This then gives us a way of calculating, for any point in space, the electric field. But it also gives us a way of measuring it. Suppose we come out to some point in space here and don't know about the locations of any charges. We can measure the electric field by measuring the force on a test charge and using this equation to define the electric field from that. So let's do it. Here we have a test charge, and I think you can see that the string is not vertical. There is an additional force other than gravity on this charged body. Where is it coming from? Over here is a charged Van de Graaff generator. And the electric field produced by this charge exerts a force on this test charge at this point. Now, these two representations are essentially equivalent. That is, for electrostatics, we can consider either the force between two charged bodies or the force on the test charge due to the electric field of the other. Yes?
If this sphere is positively charged, it's surrounded by an outwardly directed electrostatic field. A positive charge placed here would be driven outward, a negative one would be attracted. If the polarity of the charge on the sphere were reversed, the forces would be reversed. For example, if we consider not a free test charge, but the charges in the little metal wires of this needle, we could consider the forces acting on them. If the sphere were positively charged, the negative free electrons would be attracted to this end, leaving the other end positively charged. If the polarity of the sphere were reversed, the electrons would travel to the other end. And if we had an alternately charged sphere, we could produce in this wire an alternating current. This is just the kind of thing that happens in a radio antenna. Here is a little pocket radio.
Weather, it'll be cloudy tonight and fair tomorrow, in the 40s tonight and near 6.
The signals that you just heard were produced by an oscillating electric field which produced an alternating current in this antenna. These were amplified in the radio and produced the sounds which you heard. This brings us to a crucial point. When we are dealing with radio waves and oscillating electric fields near a receiving antenna produced by distant oscillating charges on a broadcasting antenna, Coulomb's law is inadequate. But if we are considering fixed charges For instance, on a Van de Graaff generator or on a pith ball, Coulomb's law is adequate for the computation of the constant electric fields. Here is the picture of the electric field around a positively charged sphere. These lines, which are called lines of force, indicate the direction that the force would act on a positive charge held at any point in the field. For example, we could use a positively charged pith ball, and if we held this in the field, it would have a force exerting on it so that it would swing out. This sort of device is often not very convenient for measuring electric fields, and we have made little gadgets of this kind where we have two pith balls which we needn't charge. The electric field itself induces a charge. You see, the free electrons in the conducting wire between them are attracted towards this positive charge, leaving this sphere negatively charged and this one positively charged, and there therefore would be a torque acting on this little suspension if it were not exactly parallel to the field. And this torque would act until the little indicator here, which is really an electric compass, would show us the direction of the field. A device of this kind can be used to explore electric fields more generally. For instance, a much more interesting electric field is that which we would have with two charges present, as on this next diagram. Here we have a plus charge and a minus charge. You notice that in the vicinity of the plus charge, the lines go radially outward, just as they did on the previous picture. That is because the field here is dominated entirely by this local charge and is affected very little by the negative charge over here. If, however, we come to other regions of space, for example here, where the two charges are equidistant, the field is very much distorted. And we could actually show by calculation that this would be the expected direction. For example, if we put a little positive charge here and performed a test, we would find a resultant force in this direction because this positive charge will exert a force radially out in this direction. This negative charge would exert an attractive force in this direction, and the resultant of those two forces would be a horizontal force off in this direction, which you see is tangent to this line of force, so that this line of force indicates the actual direction of the force on a test charge. This diagram now shows the direction of the resultant force on a test charge at any point of the diagram. And these lines of force, you will notice, originate on plus charges here and terminate on minus charge. This is a perfectly general property of lines of force. They always do in electrostatic problems, originate on a positive charge and terminate on a negative one. Another example of a field that we might explore is one in which we have two positive charges, as for example on this third picture over here. Again, we see that the field in the vicinity of either one of these charges is predominantly radial and is distorted from this radial configuration only when we reach these points of space from which the two charges are more or less equidistant. And here you see we have an entirely different situation. Instead of being horizontal, as in the previous case when we had opposite charges, it's radially outward, and we can compute this again. You see, if we have a positive test charge here, there will be a repulsive force in this direction, and due to this one, there will be another repulsive force in this direction, and the resultant of those two would be a force in this direction, which is the direction of the lines of force in this representation of the electric field. Let's now have a look at some actual fields.
Well, here we have two spheres that we can charge at will in a whole forest of our little indicators. Let's see what we can do with them. First of all, let's have a little air, a little fan. Blow them around a little bit so you can see that they're all free to move. And incidentally, to get a random pattern, now we'll charge this sphere positively. And I think you can see all these indicators in this region pointing inward toward the sphere, indicating that the lines of force go in perpendicularly. Now we'll charge this sphere negatively. Now you can see that we have a general pattern of lines which tend to start at this sphere and go all the way across to the other one, starting from here and going around there, and from there and going around there, and similarly on this side. Now, let's try something a little different still. We'll discharge both of the spheres and blow with our fan again to jiggle things up a little bit. And this time we'll connect both spheres to the same potential. Put the same charge on both spheres, so that they are now going to receive the same charge, and we'll charge them both positively. Now this time, I think you can see that the lines of force are a good deal different. If we start from here and move out in this direction, we have lines of force going out more or less this way. And similarly, from this sphere, they go out in this direction. And the same way over there. They tend to go out that way and that way. You'll remember when we had them, this one negative and this one positive, the lines of force started at this sphere and went over to the other. And now we have something quite different.
So far, we've been considering electric fields in space. Let's now turn our attention to electric fields inside of metals. Metals, for our purposes, may be thought of as substances in which there are free electrons. Charge is free to move. Metals carry currents. And in terms of the electric fields that we've been discussing, we must conclude that whenever we have moving charges, we must have fields which push them around. And conversely, if we are dealing with electrostatic problems in which charges are at rest, the fields inside of a metal must be zero. This idea is rather hard to think of in detail. Let's illustrate it in the case of this particular cylinder here. Let's imagine that we have here an accumulation of plus charges and here minus charges, which produce an electric field with horizontal lines of force across here. Now what happens when we introduce this metal? There are free charges in it. Excess negative charge will be attracted toward this side where we have plus charges and will accumulate on this surface and leave this surface here positively charged. This is all in accordance with what we've said. But what we must conclude now is that the particular configuration of charge on these surfaces must be such that the sum of the fields due to all the charges present, these out here plus those on the surface, must give a zero field on the inside of this metal. It may seem strange at first that this can happen at all, but it can be experimentally shown to be the case, and we can demonstrate it, not in the case of this solid cylinder, because we can't get inside it to make measurements. But we can hollow away the inside of this solid cylinder without disturbing the field due to the charges on the outside, and then actually make measurements of the field which they produce.
Here on the outside, we have relatively strong fields, the indicators pointing inward toward the metal cylinder. On the inside, there is no field. The indicator assumes no fixed direction but continues to rotate. If we remove the cylinder, the indicator ceases to rotate and oscillates back and forth, eventually coming toward a line of force between the two spheres. Now we can put the cylinder back again. The indicator ceases to oscillate and starts rotating again, showing there's no force on it. Now we remove the cylinder again, and it comes to rest along a line of force extending from one of the Van de Graaff spheres to the other.
Here we have another metal cylinder. In an electrostatic problem where no currents are flowing, regardless of the charge distribution in its vicinity, there must be a charge distribution on the surface of the cylinder so that the resultant field inside is zero. The situation is, however, entirely changed when we draw a current. If I fasten this cylinder to a circuit, for instance by having a current come along a wire to this end here and going out from that end, we must have a an electric field inside of this cylinder parallel to the current, parallel to the axis of the cylinder to make the current flow. In order to demonstrate this, we must again use a hollow cylinder so we can put a test charge in it, and moreover, the cylinder must be transparent so that we can see the behavior of the test charge.
Here we have just such a transparent hollow conductor. This is really two glass tubes, one inside the other, and in the space in between the two glass tubes, there is a liquid conductor. In the space inside the inner glass tube, we have our little electric field indicators so that you can see the direction of the lines of force. Now we're going to pass current through this transparent conductor, and you can see it indicated on the meter. But first, we're going to put the whole apparatus in an external electric field caused by these two charged spheres. You can see the effect of the external electric field on these indicators. Of course, it does not penetrate to the inside of the conductor because there is no current flowing. Now we're going to pass a current through this conductor, and the electric field due to that current, which you can see on the milliammeter, will cause these indicators to line up along the axis. Now, the field is very weak and the force is very small, so it takes them a long time to come to equilibrium, but I think you can see that they're about to do so.
Whenever we have currents flowing along a wire, we must have electric fields to drive them. Not only in the case of a long, straight cylinder such as we've seen, but even in the case of a complicated wiring system such as we have here. At every point where there's a current flowing, there must be an electric field to drive it.
Let's see what happens to the field inside a conductor which is not straight when we connect it to two oppositely charged generators so that a current flows through it. See? They're all lined up, each one pointing along the axis of the bent conductor.
We have seen that electric fields in conductors produce currents. Conversely, whenever there is a current in a metal or in a wire, there must be an electric field to drive it. This puts us in a position to verify a point that I made earlier in this film. I spoke of electric fields, oscillating electric fields, being associated with radio waves. Here before me in space, there is an incoming radio wave with a horizontal electric field. I can demonstrate it with this apparatus. Here we have two wires insulated from each other but connected to a little electric light bulb socket. Dim the lights and let's put in the bulb. You notice that when I held this antenna horizontally, the electric fields drove currents to and fro through the bulb and lighted it. When I turned it into a vertical position, the horizontal fields no longer could do this. The electric light bulb was lighted by a very strong oscillating electric field radiated here in this room. Much weaker oscillating electric fields are present here and all around you as well. These weaker fields require for their detection more sensitive equipment. I told you at the beginning of this film that Coulomb's law was inadequate for the description of all electrical phenomena, that we needed the idea of electric fields, and that oscillating electric fields were present everywhere, in the space around the charges in atoms, between atoms in the air, and out in the sky. We're now in a position to demonstrate this, since we've shown you that invisible electric fields produce observable electric currents. This radio telescope consists of a giant reflector that focuses the incoming radio waves at the center. Here, the oscillating electric fields produce currents that are fed into the building where they are amplified and recorded. This particular hump in the curve was produced as the telescope swept through a certain region of the sky. These signals came from a nebula, the Crab Nebula. They were generated by moving charges out there hundreds of years ago and have been traveling through outer space, out beyond the solar system, toward us ever since.
If you look at a radio transmitter, at a tube that conducts a fairly large electrical current, you'll discover that certain parts of the tube can be made hot enough to glow. The plate of this tube is heated bright by the energy of the electrons that smash into it. Today I want to use the heating of a plate in a vacuum tube to check up on the energy flow in an electric circuit. The energy we're going to be concerned with is the energy of a moving elementary charge acted on by an electrical force. Perhaps you'll remember the equipment we used in the Millikan experiment. These plates are the essential part of that apparatus. We used them in an experiment similar to that done by Robert Millikan when he investigated the existence of elementary charges by measuring electric forces on them. The plates are almost exactly 3.1 millimeters apart. 3 batteries were connected across the plates. We bombarded the region between the plates with X-rays. This made it possible to add elementary charges or to subtract them from the tiny little standard spheres that we let drift down between the plates. By measuring the rate of ascent or descent of these spheres, we were able to determine the force on an elementary charge in the electric field between the plates. We came out with a force of 1.4 times 10 to the minus 14th newtons per elementary charge. You'll remember that in the Millikan experiment, the little standard spheres with the charges on them come down through this hole into the space between the plates. Also in that experiment, we had 3 batteries, each of them 90-volt batteries, connected between these plates. In the Millikan experiment, the charges, the elementary charges, are on those little standard plastic spheres you saw. We want to get rid of those spheres so as to be sure that the gravitational force is negligible and we're dealing only with the electrical force. In place of these standard spheres, we're going to boil out some electrons from a filament. We'll place it here above the hole or next to the hole. Better have a little bigger hole. The filament is tied to this plate. We do that so that there's no electrical force between the filament and plate acting on any charge there. Since gravitational force is negligible, there's essentially no force on electrons boiled out in this region. Nevertheless, some of the electrons go through the hole and get in here between the plates. There, they are attracted toward this plate because we're going to have the positive terminal of these batteries here and the negative one up here. The force here is therefore 1.4 times 10 to the minus 14th newtons per elementary charge. That's the force in this modified apparatus. Now, Bjorn Madsen of the Institute of Theoretical Physics in Copenhagen has built this kind of apparatus. In his equipment, this plate's actually thinner than we've shown here. Perhaps this one is thicker. Also, the whole thing is in a glass tube, closed glass tube, with the air pumped out. So there's nothing in the way of the charges as they move across here between the plates. Here you see the essential parts of that modified Millikan apparatus. On the left is the filament. Electrons from it pass through a hole in the thin plate and are accelerated across the 3.1 millimeter gap, crashing into the copper plate on the right. Each electron gains a definite amount of kinetic energy. We should be able to compute how big that kinetic energy is because we know the force on a charge between these plates, and we know the distance between the plates. We just multiply the force times the distance. This is our prediction for the energy, the kinetic energy gained by each elementary charge. Now, when I know the energy for each elementary charge, I can find out what the energy is per second. If I know how many elementary charges go across per second between the plates, all I have to do is to multiply the number of charges crossing per second by the energy of each charge. It's easy enough for me to find out how many charges go across between these plates. All I have to do is to put an ammeter in the circuit here. That counts the number of charges passing per second. That number of charges is the same as the number of elementary charges passing between the plates. Now, you know that we can calibrate an ammeter by an electrolysis experiment. And in the course of such an experiment, we pointed out that 1 ampere means 6.25 times 10 to the 18th elementary charges going by per second. Six 0.25 times 10 to the 18th elementary charges per second is 1 amp. We're going to choose to let 2 milliamperes flow through this circuit. 2 times 10 to the minus 3 amperes. That'll be our current here. And that's the same thing in terms of elementary charges per second as the product of these two numbers. 12.5 times 10 to the 15th elementary charges per second will be the current. Let's write that down. I'll write a little differently. 1.25 times 10 to the 16th elementary charges per second. That's the current we're going to allow to go through here. Now, when this number of elementary charges is flowing through, and each one is bringing this amount of energy to the thick copper plate, and the amount of energy per second brought to that plate is just the product of these two numbers. That's about 5.4, 10 to the minus 1 joules per second. Now, in Madsen's apparatus, it's convenient to run for something like 20 seconds and to get an energy transferred into the thick copper plate of something of the order of 10 joules. We can do that by picking a time of between 20 and 21 seconds. Then, since this is the energy per second, and that's the length of time, the product of those two is almost exactly 11 joules. This is our prediction of how much energy will be transferred into the thick copper plate when we run with a current of 2 times 10 to the minus 3 amperes for a time between 20 and 21 seconds. Now, this blackboard is covered by a morass of numbers from all kinds of sources. Seems to me to make it a little hard to see how really simple the reasoning was by which we arrived at our prediction. These 11 joules of energy that were going to be brought into the thick copper plate. I want to see whether I can't put it together so you can see really what was the simplicity of what we've just been through. What did we really do? Well, we took the force per elementary charge. And we multiplied it by the distance that each elementary charge goes through from plate to plate. That gave us the energy, the kinetic energy with which each one of the electrons should crash into the thick copper plate. To find the energy per second, all we had to do was multiply by the number of electrons, the number of elementary charges per second. That's the current. That gives us the energy per second coming into that plate. Now, to get the total energy, all we need to do is multiply by the time in seconds. This should then give us the total amount of energy in the course of the whole experiment brought in by the electrons crashing into the thick copper plate. The 11 joules we calculated earlier. Well, that's a prediction. But how do we check up on it? Well, you know that there's a relatively simple way of finding out whether that energy actually comes into the thick copper plate. I can illustrate the idea this way. If I take this piece of lead and really whack it hard as I can with a hammer, lead heats up. The thermometer really rises. I could even feel it. I didn't need to do that for you. You knew what was going to happen. But it was fun, and it makes the point. The kinetic energy of the hammer was transferred into internal energy of the lead and a bit into the hammerhead. A definite part of the energy goes into raising the temperature of the lead. And from an experiment such as Joule did, we know that an accurate measurement of that temperature rise will tell us the kinetic energy of the hammer at the time when it hit. Now we're going to use the same kind of procedure, essentially the same thing we just did, measure the kinetic energy of the electrons rather than the hammerhead. The kinetic energy of the electrons when they whack into this thick copper plate in the tube. We'll use these two pieces of wire instead of a thermometer. They make up what is called a thermocouple. We embed the thermocouple in a hole in the plate. As you can see with this partially assembled tube, the wires from the thermocouple go to this sensitive meter. If we warm up the thick copper plate slightly, and wait a few seconds for the heat to flow around in the copper, the indicator on the meter begins to rise. Stop warming the copper. Soon the heat is distributed evenly, and the meter stops rising. Now I think we're ready for the main experiment. The meter is connected to the thermocouple in the complete tube that Masson made for us. This is the battery that will heat up the filament. Now he connects it to the tube. Here are the three batteries that are connected across the two plates in the tube. This wire passes through a meter to read the current that will flow, then through this switch to the copper plate. Now Masson connects the batteries across the plates long enough to adjust the current flowing from filament to plate, so that that current will be 2 milliamperes, as we mentioned before. Then he cuts off this current until he's ready to start. He'll need to use a stopwatch to make sure that this current is allowed to flow for about 20 or 21 seconds. A check of the thermocouple meter shows that the temperature of the copper plate is steady. The indicator stands still, right at 28. Now Masson switches in the batteries. The current flows. The indicator line begins to move on the thermocouple meter. The electrons crashing into the plate are heating it up. The indicator's moved about 10 divisions to 38. Now the temperature rise has caused the meter to move about 18 divisions. It's time to cut it off. The plate stops heating. Meter comes to rest at about 52 divisions, a rise of about 24 divisions. This rise is just about what Masson gets every time he tries this experiment. So now we can say that with this apparatus, we've shown that the energy brought in here to this thick copper plate in the tube is enough to cause it to heat up, making the meter deflect by about 24 divisions. That's what we've shown. Earlier, we predicted that we should have 11 joules of energy brought into that plate in this experiment. But we haven't proved that that's the amount of energy. Now, what do we have to do to make sure that we've got 11 joules coming in here, or to find out that we're wrong? Well, one way is to get, independently, a package that we're sure is exactly 11 joules and transfer it to the thick copper plate and see whether we get a deflection of about 24 divisions. To get such a package is actually a cinch. Andy Littell probably has one waiting for us in the next room. Now, if I drop this mass, 1.5 kilograms, through a distance of 3/4 of a meter, it should acquire 11 joules of kinetic energy. That's about 3/4 of a meter off the floor. That was very much like the electrons crashing into the plate of Masson's tube. The only difference is that the force here is gravity. Now, we really don't have any reason to put our 11 joules into the floor. It doesn't do us any good. What we really want is to put this guaranteed package of 11 joules into the plate of Masson's tube, or into a plate that's exactly similar. Now, we can do that. This apparatus that Andy's got here is made just for that purpose. He's attaching the mass to this string here. The string comes up over this axle. At the end of the axle is a plate, just like the one in Masson's tube. This plate can be pushed up against another similar plate to its left. The axle with the plate attached to it can be turned. The plate on the left is fixed in place. By turning the axle, we can wind up the string and lift the mast to any height we want. Here, for example. Now Andy's going to put in a spring which forces that axle toward me. This presses the two plates tightly together. Now let's see what happens when I let the mast go down again. This time you see it goes slowly, unlike the time when I dropped it. That's because the energy is being rubbed off here, going into heat in the plate and in the similar one, just the way we wanted it to. If I rub my hands together the way those plates were rubbing together, I can dissipate energy into them, heating them up. If I want to dissipate 11 joules of energy in this hand, for example, I'd better dissipate a total of 22 between the two of them, because half of the energy will go into this hand, 11 joules, and the other half into the other hand. We'll have to do the same thing with the plates, as they take the energy given us by the falling mass. So we'll have to get a package of 22 joules of energy from the falling mass. That means we want to start it not 3/4 of a meter off the floor, but 1.5 meters off the floor. Andy's clearly figured that out. This line is 1.5 meters off the floor. When he's got this mass up here, as it falls, it'll dissipate 22 joules of energy through the rubbing of the plates, one on each other, on the other. 11 joules will come into the left-hand plate, which is just like the plate in Masson's apparatus, and be picked up as a temperature rise by a thermocouple right there, let out through these wires down here, over here, to exactly the same thermocouple meter that was used when we measured the energy that the electrons brought into the plate in Masson's tube. Then we can see from the rise of this thermocouple meter whether 11 joules is really what the electrons brought in. Well, this part's ready. The meter is steady at about 28 divisions, so I guess we can take a run. It's rising. It's going about 10 divisions to 38. Another 10 to 48. It's still going up a bit. And now it's stopping after going about another 3.5 divisions to 51.5. That's a total of 23.5 divisions. Now you can compare that with what we got when the electrons crashed into the plate in Masson's experiment. That was about 24 divisions. Like any good experimenter, Andy's done this same experiment several times over. He always gets about the same result. So now let's see where we are. Let's go in the next room, take a look at the formula from which we made our prediction, and go on from there. Earlier today, we made a specific prediction about the energy picked up by electrons under the influence of an electric force. We made that prediction from this formula, using the force per elementary charge from a Millikan experiment. Then we checked up on it with the two experiments you just saw. Their agreement shows that the electrons crashing into the plate of Mason's tube were carrying 11 joules of energy, just as we predicted. Can we conclude from this agreement that our procedure, our formula here, is generally valid? No, nothing of the kind. A single agreement like that can always be an accident. One sunny day doesn't make a summer, even when the weatherman happens to have predicted it from his formula correctly. To get confidence that our formula really works, we should try changing the values of every factor in that formula. We can change the time. It's at our disposal. How long we run the experiment. We can change the current between the plates and through that ammeter, the number of elementary charges per second. We could change the number of batteries across the plates. And when we do that, we change the force per elementary charge between the plates. We could even change the separation distance of the plates, this factor. All those changes have been tried. For example, suppose we put double the number of batteries across the plates. Then we will have doubled the force on each elementary charge. At the same time, we might cut the current through the ammeter in half. We might leave the time and the separation distance of the plates alone. 2 times the force and half the current happens to give a prediction of just the same energy transfer, the 11 joules that we had before. But the situation is entirely different. Let's see if he still gets about 24 divisions on the thermocouplometer. The meter is steady now at 20. Mason runs the new experiment. The pointer starts at 20. It moves up. Now about 10 divisions to 30. To 35. Now he disconnects the batteries. It's past 40 to about 43. A change of 23 divisions. That's as close as we could reasonably expect to come to what we had before. The formula worked again. This time with twice the force we had in Mason's first experiment and in the Millikan experiment, and half the current. And it works over and over, the whole procedure. We've tried it with all sorts of different values. Other people have tried it this way or with other equipment. Our predictions keep coming out. So now it's time to believe. We've really got hold of the right way to predict the energy transfer to moving elementary charges from electric forces. What does it all mean? What's behind it? I want to pay a little attention to that for a minute or two. For example, in Mason's last experiment, the force was twice per elementary charge what it was in his first experiment. The distance between the plates, the distance through which the charges move, was just the same. With twice the force accelerating the charge through the same distance, it's going to end up going faster, going about 1.5 times as fast. Prediction worked, but nowhere in it did it say a thing about the speed. The fact that at these different speeds we were able to predict suggests that the force probably has nothing to do with the speed. It's independent of it. We can make that point a lot stronger. Suppose we compare Mason's first experiment with the Millikan experiment, where the forces were just the same on each elementary charge. In Masson's experiment, the charges went across vacuum. They wind up crashing into this plate at tremendous speed, about 10 to the 7th meters per second. Contrast that with the Millikan experiment. There the charges were on the little spheres, and you saw them just dawdling along, practically no speed at all, under the same force. Force is independent of the speed, at least in this kind of a situation, where the source of the force, the charges on these plates, is standing still. Now, we made the assumption, without thinking about it, that the force was independent of speed. It's quite a natural thing to do. But we really must check up on it in some such way as we've just done. Let me show you the necessity of checking up on such assumption. For example, take another situation. The force is produced by a charge which happens to be moving, let's say here, and it acts on another moving charge over here. We might just as well assume the force between them depends only on the separation. But we'd be wildly wrong. In that situation, there's a new force, the magnetic force, which you're going to study about later. So it's really necessary to check up on such apparently obvious assumptions. And we've really learned something here, namely that when the source of the force, the charges on the plates here, are standing still, the force on the moving charged particle is independent of the speed of its motion. Now, there's just one more thing that I'd like to talk about for a moment. You may have thought about it already. In this experiment, we've been relying on the force per elementary charge from the Millikan experiment. And on the other hand, we've been counting the number of elementary charges in a completely different way with this meter, and it's calibrated by an electrolytic experiment, relying on the ideas and experiments of Faraday to count the number of charges in terms of the unit of charge that he saw in electrolysis, brought over by ions going through liquids. We might call that unit a Faraday elementary charge. The two things are quite different, the Millikan experiment and the Faraday experiment. Are the two elementary charges the same or different? We've been assuming that they're the same. Let me show you where we put that assumption in. Here's the force per elementary charge from the Millikan experiment. Here is a Millikan elementary charge. Here we were counting, with the ammeter, Faraday elementary charges. We took these two elementary charges, the Millikan and the Faraday elementary charge, to be the same. We made our predictions on that basis, and those predictions agreed with experiments. If the Faraday elementary charge and the Millikan elementary charge were different, then the actual observations should not agree with our predictions. So we've proved from a series of observations and the agreement with prediction again and again that this elementary charge is the same as that one. There's really only one elementary charge in nature.